Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, New Delhi. Today we are going to discuss about a module called Characterization of Fluorescence Emission under paper entitled Characterization of Materials 2. So students, let's see what we are going to learn in this module. First, the fundamental physics of emission of light. Second, various processes for emission of light from materials when exposed to different external energy sources. And third, we will find the rules to understand the emission of light. As an introduction, the luminescence informs the properties and applications of different types of luminescent materials, and luminescence is a science closely related to spectroscopy, which is the study of general laws of absorption and emission of radiation by matter. Luminescence quantifies several advantages over other analytical techniques, and this process is extraordinarily sensitive, and we can do experiments in a very wide dynamic range. And these techniques is very inexpensive and uses instruments which are readily available. Superior sensitivity and low background distinguished luminometry from other analytical methods, and luminometry is 100,000 times more sensitive than absorption spectroscopy, and it is at least 1000 times sensitive than the fluorometry. Photoluminescence spectroscopy is one of the most powerful and useful optical method for characterizing the semiconductors, and various industries are using these techniques to analyze the intrinsic and extrinsic properties of semiconductors. With its powerful and sensitive ability to find impurities and defects in various semiconductors, specifically in silicon and group 3-5 semiconductors, which affect materials quality and device performance. Photoluminescence spectroscopy is also a powerful technique for investigating the electronic structure, both intrinsic and extrinsic, of semiconducting and semi-insulating materials. And photoluminescence performed at room temperature or at very low temperature with a tightly focused laser beam. This technique has much advantages over absorption, and which is having difficulties because of requirement of a broadband excitation sources such as tungsten halogen lamp, while photoluminescence can be performed with any light with energy that could provide above band gap laser sources. For thin film samples, absorption spectroscopy requires that the substrate be etched away to permit transition of light through the sample, but for bulk samples, the transmitted light may be quite weak, creating signal to noise ratio difficulties. Origin of energy states in materials. All materials consist of atoms of various elements containing movable electrons and localized nucleus. The optical and optoelectronic properties of the materials depend mostly on the activities of the electron and their responses toward the externally applied energies at different energy environmental conditions. The negatively charged particle electron has a specific orbitals with definite energy defined in the atom where they can stay. In the energy spectrum, the atomic or molecular orbitals are the available energy states permissible for the existence of electrons. This could be understood by considering electron as a particle experiencing the confinement potential in the dimension of the atom, and the resulting quantum mechanical system yields discrete energy levels due to the quantum confinement effect and referred as electronic energy states. The energy spectrum of the quantum mechanical systems with such discrete energy levels is said to be having quantized energy levels. The atoms, ions, and molecules are demonstrated as quantum mechanical systems, and in equilibrium, the electrons like to be in a low energy state referred as ground state, as shown in the solid blue line in figure 1. If the electron stays at a higher energy level than the ground state energy, then the energy level is referred as excited energy state. Generally, the electrons in atoms, ions, or molecules are bounded by the electric field of the nucleus and can also have the nuclei or vibrational or rotational energy levels in the energy spectrum, in addition to the electronic states. The vibrational, ground state, or each electronic state are indicated with thick and dark lines. The higher vibrational states with light colored lines have been shown in figure 1. So, the total energy of the molecular state can be written as energy of the electronic states plus energy of vibrational states plus energy of rotational states plus energy of translational states plus nucleus or nuclear energy level. The transition of electrons within the allocated energy states gives rise to production of light artificially. There are two different kind of processes. First is incandescence. This is the light emitted from the heat energy produced by the excessive temperature within a material. When a material is heated to a high temperature, it begins to glow, and the process is termed as incandescence. For example, electric heater or metal in flame begin to glow red hot and the glow of sun and stars. Second type is called luminescence. Here, the luminescence is light emission due to an excited energy. If some external energy is supplied to any luminescent material, the supplied external energy moves the electron from a certain baseline energy known as the ground state to a higher energy state called excited state. Then the electron falls back to its ground state by emitting its energy in the form of light. Generally, the excitation energy is greater than the energy emitted by the electron. Luminescence is described by light absorption and emission and could be defined as below. Luminescence is described by light absorption and emission processes and could be defined as absorption and emission. In the absorption process, this is the process in which electron absorbs the incident photon and jumps to an excited state called absorption. The energy of incident photon must be equal to the energy difference between ground state and excited state. The absorption is shown in the figure 1a. Absorption spectrum is also referring as excitation spectrum. The emission process is the process in which the excited electron loses its energy by emission of photon and comes back to its ground state called emission. It is shown in the figure B. The luminescence process could be defined in various types depending on the source of the excited energy and as discussed below. The luminescence processes are various kinds. First is chemiluminescence, which is a result of chemical reactions. It includes bioluminescence, where luminescence is produced during biological reaction by a living organism. Second is electrochemiluminescence, where the luminescence is produced during electrochemical reactions. The other type of luminescence is crystalloluminescence, which is as a result of crystallization process. Electroluminescence is as a result of electric current passes through a material, and it includes cathodoluminescence, where the luminescence is produced during the luminescent material being struck by the electrons. Mechanoluminescence. This is activated as a result of mechanical action on a solid. It includes triboluminescence, where the luminescence is produced by bonds in a materials which are broken when it scratched, crushed, or rubbed. The second type is fractoluminescence, where the luminescence process is produced due to bonds in a certain crystals are broken and fractures. Piezoluminescence, where the luminescence is produced by imploding bubbles in a liquid when excited by sound. Radioluminescence is as a result of bombardment by ionizing radiations. Thermoluminescence is activated as a result of heating of a substance, and that includes cryoluminescence, where the luminescent process is produced when an object is cooled. The another type is photoluminescence, where the activation process is as a result of light exposure to the materials, and the luminescence is produced when the material is excited with monochromatic light. Photoluminescence process. This is a process in which light is emitted by absorption of photons. After exciting the electron from ground to the excited state, the relaxation occurs and the electron falls back to its ground state by emitting light. If there is no allowed transition possible for an electron to transit from an excited state to any lower energy state, it remains in the higher energy state for a relatively longer period. Such states are termed as metastable state. Photoluminescence is the process in which Light is emitted by absorption of photon. After exciting the electron from a ground state to excited state, the relaxation occurs and the electron falls back to its ground state by emitting light. During this process, if there is no allowed transition possible for an electron to transit from an excited state to any lower energy state, it remains in the higher energy state for a relatively longer period. Such states are termed as metastable state. Depending upon the nature of the emitted electron, the photoluminescence process can be defined in two ways. First, fluorescence. Here, the luminescence process is produced as a result of singlet-singlet electronic relaxation. Second, phosphorescence. Here, the luminescence is produced as a result of triplet-singlet electronic relaxation. Fluorescence. In this process, the materials absorb light at a particular wavelength and emit light at a longer wavelength than the incident light. This process can also be explained as absorption of light of electromagnetic radiation at a frequency nu and emits light at a lesser frequency nu prime when nu is greater than nu prime. Fluorescence refers to immediate release of light. The light is emitted within a fraction of a second after excitation, and the fluorescence process is sketched in the diagram. The materials showing fluorescence behavior are called fluorophores. Depending on the difference in energies between the ground state and excited state, the fluorophores absorb lights of different wavelengths, hence it has specific absorption spectra, and similarly they have specific emission spectra. Possible spin states: absorption of ultraviolet or visible photon promotes a valence electron from its ground state to an excited state, and the phenomenon is called excitation. The excited state, where an electron retains its spin, is called singlet excited state. When the spin of the excited electron changes with respect to the ground spin state, then it is called triplet excited state. The schematics are shown in the figure, but the excited electron is not stable and cannot stay in the excited state indefinitely and returns to the ground state with the emission of a photon. This process is called fluorescence. The average lifetime of the electron in the excited state is only 10 to the power minus 5 to 10 to the power minus 8 second. Here, the wavelength of emitted photon is longer than the wavelength of observed photon, that is, lambda prime is greater than lambda. Fluorescence decays rapidly after the excitation source is removed. Basic principles of fluorescence: the materials showing fluorescence follow certain rule. First is Franck-Condon principle, second Stokes shift, and third is mirror image rules. First, Franck-Condon principle: the nucleus has much greater mass than the electrons, so that during the electronic transition the nucleus remains stationary but electronic configuration changes. Therefore, the internuclear separation remains same after absorption. So according to this principle, the most intense electronic transition occurs between the vibration states that arrange vertically in the different electronic state, so that the nucleus remain stationary. Classically, the Frank-Condon principle says that the transition of electrons from the ground state to the excited state occurs without any change in the position of the nucleus. This promotes the ground state electrons to the excited state through vertical transitions and plotted as vertical lines in the figure. Stokes shift. In this process of luminescence, after absorption of incident light, the electron goes to an excited state and falls back to the ground state with the emission of light having lower energy than the observed light. Therefore, the emission spectra move towards the longer wavelength and a shift is observed in absorption and emission spectra. This shift in wavelength delta lambda is called Stokes shift or governed by Stokes law. The fluorophore emission intensity peak is usually lower in magnitude than that exhibited by the excitation peak. As Stokes shift value increases, it becomes easier to separate excitation from emission light using fluorescence filters. The Stokes shift occurs due to the loss of energy to bring the excited electrons to the lowest vibrational energy level of the excited state from the highest vibrational energy levels. In addition, fluorescence emission is usually accompanied by transitions to higher vibrational energy levels of the ground state, resulting in further loss of excitation energy to regain the lowest vibrational energy level of the ground state. The total loss of energy observed during the emission process is a combined loss of energy of electron in the excited state before emission and in the ground state after emission. Other events such as solvent orientation effects, excited state reactions, complex formations, and resonance energy transfer can also contribute to longer emission wavelengths. The excited state is termed as S1 in the figure and the ground state is denoted as S0. In practice, the Stokes shift is measured as the difference between the wavelengths at a maximum peak intensities in the excitation and emission spectra of a particular fluorophore. The amount of shift varies with molecular structure and can range from few nanometers to over several hundred nanometers. For example, Stokes shift for fluorescein is approximately 20 nanometer. The shift for quinine is 110 nanometer and for the porphyrins it is over 200 nanometer. Mirror image rules. Generally, it is seen that the electron which goes to the higher energy state with the absorption of photon undergoes same transition during the emission. Here, the emission spectra is mirror image of the absorption spectra. The emission spectra are the mirror image of absorption spectra during this transition from the ground state to the first excited state. Same transition occurs between ground state and first excited state, shows the similarities of vibrational levels of ground and first excited states. Exceptions of the mirror image rule. Deviation from the mirror image is observed for transition to excited states higher than the next excited states. As an example, the excitations from ground state S0 to S2 or S3, second excited states or third excited states. Excitation by higher energy photons leads to transition of electrons from the ground state S0 to the higher electronic and vibrational levels of S2 and S3, etc. The resulting population of electrons in the higher energy states rapidly loses the excess energy and relaxes to the lowest vibrational level of that specific excited state, followed by transition to the first excited state S1, and finally comes back to the ground state, so that the emission spectra are not similar to excitation spectra, and the higher excitation states do not follow the mirror image rule. Here we will see few uses of fluorescence. First, we are using in daily life. While the marks made by fluorescent highlighters quickly draw our attention to important points in a document, fluorescence is also useful in a number of safety applications as a scientific research tool and in investigative medicines. Fluorescence is also useful in binding studies for biosensors. The use of fluorescence spectroscopy can provide important information about the process of ligand binding and ligand dependent conformational changes in receptors. Fluorescent based techniques are rapidly becoming widely used to address fundamental and applied questions in the biological and biomedical sciences. Medical research makes widespread use of fluorescence to understand biological process and in diagnosis. Phosphorescence. Phosphorescence is a type of luminescence where the emission process continues for a noticeable time after taking off the incident excited radiations. When a substance exposed to radiation, it emits light and persists to glow for some time after the exciting radiation is removed. In fluorescence, the observed light is spontaneously emitted about 10 to the power minus 8 seconds after excitation as compared to phosphorescence, which requires about 10 to the power minus 3 seconds or days or years depending on the circumstances. The working principle of phosphorescence. In some materials, there exists an intermediate energy state between the ground and the excited states referred as metastable state or electron trap. Once an electron falls from the excited level to the metastable level by radiation or by energy transfer to the system. It remains there until it makes a forbidden transition or until it comes back to the ground level by losing energy through thermal agitation among the neighboring atoms or molecules called thermoluminescence, or through optical emission. This makes slow transition of the electrons in the metastable state to come to the original ground state by spending more time in the metastable state or electron trap that determines the length of time for phosphorescence. The total spin of the electrons in the excited state is 0, while the total spin of the electrons in the metastable state is 1, as shown in the figure. The multiplicity can be calculated by the formula m is equal to 2s plus 1, which for the excited state is 1, termed as singlet state, and the multiplicity of the metastable state is 3, termed as triplet state. The transition of the electrons from ground state to a metastable state is forbidden because it violates the selection rule for conservation of spin, that is delta S is equal to 0, and can transit from the ground state to an excited state. Most of the electrons immediately hop back to the ground state by radiating or emitting energy in the form of photons, but non-radiative processes takes the electrons to a less energetic triplet state. Once these molecules get to the lowest triplet state, they are stuck there at least for a while. Then the electron first flips its spin and then come back to the ground state. Uses of phosphorescence. Phosphorescent materials are used in a wide variety of applications and products. For example, fluorescent powder and gel can be found in many different toys such as glow sticks and other glow in the dark products. The majority of phosphorescence is often used in drugs in pharmaceutical field. Some common drugs that have phosphorescence property include aspirin, benzoic acid, morphine, and dopamine. Phosphorescence is also used to analyze water, air, and chemical pollutions. So students, let's see what we have learned in this module. We have learned about the fundamental physics of emission of light, various processes for emission of light from materials when exposed to different external energy sources, and there are two processes where we can have emission of light. First is incandescence and second is luminescence, where this luminescence depends on absorption and emission of light, and depending on the time of luminescence, we divided the luminescence process into two. One is fluorescence and second is phosphorescence. And the rules to understand the emission of light is also described. First principle is the Franck-Condon principle, where it shows the nucleus has much greater mass than the electrons. So during the electronic transition, the nucleus remains stationary, but electronic configuration changes. Therefore, the internuclear separation remains same after absorption. So this principle states that the transition of electrons from the ground state to the excited state occurs without any change in the position of the nucleus. The second rule is the Stokes shift. It tells about that during luminescence, when the electron falls back to its ground state, with the emission of light having lower energy than the observed light, therefore, the emission spectra moves towards the longer wavelength and a shift is observed in absorption and emission spectra. The third rule to understand the luminescence process is the mirror image rule that describes the emission spectra is mirror image of absorption spectra during the transition from the ground state to the first excited state. Same transition occurs between ground state and first excited state, and that shows the similarities of vibrational levels of ground and first excited states. Thank you.